In particular, let's look at some isometries. There's a well-known reflection. I use a common word, but using it in a very precise mathematical sense. It's a mapping. A reflection in a line is a mapping which assigns to any point an image point. There's an object, there's its image. There's an object, there's its image. This correspondence maps distinct points to distinct points and preserves distance. It's a mathematical reflection. Consider a rotation of the plane, where I have a fixed point, and think of the entire plane as rotating. But focus your attention on the correspondence that is produced, the correspondence between initial point and its final position. It is this correspondence which I call the rotation. Although there is a motion going on, the motion itself doesn't interest me. It's the correspondence from initial to final position that I call the isometry. A translation has the same sort of properties. Think of the entire plane as sliding. For every initial point, there is a final point. It's this correspondence which I call a translation. It preserves distance. It's one-to-one. The combination of a translation and a reflection in a line parallel to the translation is an isometry, from initial point to final point, which I call a glide reflection. A glide reflection because there is a glide and a reflection involved. So we have discussed 4 different isometries: reflections, rotations, translations, and glide reflections.
By means of isometries, because an isometry is just a mathematical abstraction of the idea of lifting up a triangle and putting it down somewhere else. Now what we want of this physical process is that everything remains rigid. Angle measure doesn't change, lengths don't change, and so on. And that's precisely what an isometry is. An isometry is a distance-preserving transformation. So the length of the sides remain the same. And it's very easy to prove that if you have distance preserving as an essential property of the transformation, then angle measure is also preserved. And this is, as I say, precisely what you want in the theory of congruence.
The person will still have to read a book and get more out of it, but I think that we can make a movie illustrating these half a dozen points.
Well, one fundamental question that always arises in producing a 10-minute film on a subject such as this is, will it have meaning? What kind of motivation do you use? Can you, in this short period of time, indicate to the viewer why anyone ever bothers with isometries?
Think of this sheet as extending over the entire plane. And suppose I apply some motion to the plane. Then a mapping is determined. Every point had an initial position, and it has a final position when the motion is finished. So this motion has determined the correspondence which assigns to every point in its initial position the point which is its final position. And it's this correspondence which I call an isometry. It has the following properties. Every point has an image. Distinct images, different points going to different points. So the mapping is one-to-one. And furthermore, the distance between any 2 points is equal to the distance between their images. It preserves distance. A mapping of the plane with these properties is called an isometry.
All the big arrows on at the same time, both lengths, or just
Oh, probably just one might do it. Maybe, in fact, maybe we should put
one
one
down.
down.
Longer one.
You we should put one down and then lift it up and move it to another, show it in a couple of positions.
Pop it?
Like that, yeah. Pop it in and out. One from one place to another.
And then move the pad.
Yeah, and then I think each time we'll put the arrows down and show which direction we're going in and do it. Put the arrows back down afterwards. And if we don't like one or the other, we'll cut it out.
Mathematically, an isometry is a one-to-one transformation of the plane which preserves distance. How do we visualize it? Well, if you think of this pad as the plane, then you may pick it up, move it around, even flip it, and arrive at a final position. Now, this motion is not the isometry. The isometry is the correspondence between the initial and final points. A point in the initial position has moved into a final position. Every point has an initial and final position in some isometry. It's this correspondence which is the isometry.
A line determines a reflection. A reflection is an opposite isometry. This means that if a point traces a closed curve in a clockwise direction, its image traces the image curve in a counterclockwise direction. An opposite isometry is sense reversing. Any point and its image are joined by a segment which is right bisected by the line of reflection. Any point on the line of reflection is its own image. All the points in this line are invariant. On the other hand, a translation has no invariant points. Since a translation is determined by a length and a direction, it is conveniently represented by an arrow from any point to its image. A translation is a direct isometry. It preserves sense. A point and a directed angle determine a rotation. The point, called the center of the rotation, is invariant. Any other point and its image are equidistant from the center. A rotation, like a translation, is a direct isometry. A glide reflection is the net effect of a reflection followed by a translation parallel to the line of reflection. Because of this parallelism, the same net effect would be produced by applying the translation first and then the reflection. Like a translation, a glide reflection has no invariant points, and like a reflection, it is an opposite isometry.
Reflection, translation, rotation, glide reflection. I have described 4 different kinds of isometries. But are these the only kinds of isometries? For example, is a product of a translation and a rotation one of these 4 types? Even simpler, what sort of isometry is obtained by taking the product of 2 reflections?
Well, why don't we just set up down the studio, we'll establish a plane, put down some tape and go along, and as we go along, I'll do it in a sense my way visually, and you tell me where we need the where the mathematics is failing. We'll just try it. We'll run through it a few times and see if we can get something. Well, let's start with the intersecting mirrors first.
Well, first of all, I draw a line of a reflection. Well, how do you get this across?
Well, we'll just put down a piece of tape to represent the... Now, do you want to put both of them down, or should we start with just one?
No, I think we'll start with one.
Okay.
Fine. Take a particular point, I'm calling it P here, and I pick up its image mathematically as follows. I drop the perpendicular to the line of reflection. I go the same distance to the other side. I pick up its image, P prime.
Do we really have to use a line in this case? Can't we, for instance, let's use those two-way mirrors. Let's set it actually on the line of reflection and look in it and see the image of the point, and put a point down on the other side and swing around and see it to see that we've established the P prime. So if I'll put the mirror down and we'll look through it, and then we don't have to put another piece of tape down to show that...
Yes, but you'll just see an image. When you remove the mirror, the image will be gone.
No, we'll put the image on the other side as well. You can see through the mirrors. And
Oh, fine. Let me now put down the line of the second reflection and find the image of P prime, that is the image of the image, in this second reflection. Again, I drop the perpendicular to the second line of reflection and go the same distance on the other side. Called the final image P double prime.
somehow or other through this, we've got to get across this notion that you've talked about of products.
Yes, well, we started with a point. We found its image under the first isometry. It happens to be a reflection in this case. Then we found how a second isometry affects this image, leading us to a final point. From an initial point to a final point, we have a mapping. And it's this mapping which is the product of the isometries. Perhaps it'll be clearer if we do this with a couple of more points. So
Yeah.
perhaps we should do that next. For example, take a second and third point, drop the perpendiculars to the first mirror to find their images in the first reflection, drop their perpendiculars to the second mirror to find the final images. Now I have 3 points and their final images, and I want to prove that this mapping is a rotation. Well, it's clear that the point of intersection of the two lines of reflection is an invariant point, so that will be the center of the rotation. To complete the proof, I require the following two properties: that any point and its image are the same distance from the center, and that the angle thus formed is a constant.
Wait, and now this will get rather involved. Could we, for instance, take the center of the or the intersection of the two mirrors, which is the invariant point, and drop down some kind of transparent material and cover these points and swing them around to show that this is a rotation. Is that enough proof? Or?
Yes, I think that would do it. It isn't a real mathematical proof, but
And then for the double angle.
well, here you could also use the transparent sheet and actually double the angle. Somehow show visually that you're doubling the angle, and then compare the angle from formed by any point its image and the intersection in the mirrors. Do this for several points to see that that angle is the same size.
Do you think we should deal with the positioning of these mirrors, that it's independent of this particular rotation? Should we show some other position of this?
Yes, well, that's a very important point. It is, any two other mirrors which intersect in the same point and have the same angle will have the same product, because it's the point and the angle which determine the product.
Yeah.
So we will have to get this across visually.
Well, maybe just take one other position.
Yes,
Just move the mirrors to another position and try to establish that we haven't changed this angle.
Yes, well,
And use the same center and go through another reflection, and then the first reflection and then the second reflection, and show
Yes,
that the initial and final positions have not.
Exactly. That's what I will want to see, that starting with the same initial point, its image will change because the first mirror will change, but the image of the image won't change.
Yeah.
If you can do that, fine. Then you really got the point across, and we have the first major theorem for us in the products of isometries. The product of two reflections is a rotation, and that rotation may be expressed in many ways as the product of two reflections. We'll need this when we analyze products of isometries later on. And then I want to do this whole thing again for parallel reflections, but there'll be some other problems coming in there.
Well, we shouldn't have too many problems. Why can't we just run through this the way that we did with the two intersecting mirrors?
All right. Here's a line of reflection. Here are 3 points, and here are their images.
we can take all 3 points this time right through, can't we? Instead of
Exactly.
Instead of starting with a single one and so on, we'll start with 3.
Fine. So we have 3 images in the first reflection, and now here's a second reflection parallel to the first one, and I see 3 images. I have 3 images in this second reflection. And now, forget or erase the intermediate points.
Now we don't need perpendiculars between the points here either, do we? Can't we just use the mirrors and find their reflections like we did before?
Certainly. In fact, that gives us right away that in this product, if you just look at the three original points and their final images, you have immediately that the join of each point and its image is perpendicular to both mirrors. But how do you get across that the length of the segment joining each point to its image is constant?
What if we took a piece of tape or some kind of measuring device, something that we could cut to the length of the distance between 2 points, between a point and its final image, and then move that over and put it on the next one and the next one and so on?
That'll do it, but then we will still have to show that length is just twice the distance between the mirrors.
You know, supposing we put the arrow or the line or whatever we use on the edge of one mirror, on the edge of the first reflection, and then put the mirror on the second line of reflection, so that we see that it's still the...
Yes, that'll do it. Now we have that the product of two reflections is a translation through twice the distance between the mirrors in the perpendicular direction. It follows this, in other words, this translation is determined by the direction perpendicular to the mirrors and the distance between the mirrors, and not just the mirrors themselves. In other words, any two other parallel reflections with the same distance between them is parallel to these two. Their product will be the same translation, and we want to get this across visually.